Armed with this rate matrix and a beginning and ending state, we can actually exactly calculate the mean first passage time using the rate matrix. We simply solve a first-order differential equation in the rate matrix, and we can come up with a notion of Arrhenius barrier, there in equation 12, and a exact mean first passage time as in equation 13. There's a big problem with this though, namely that this matrix exponentiation requires us to diagonalize it, and diagonalizing a very large matrix, especially an ill-conditioned one, takes a very, very long time. It's just not easy to do. Because mean first passage time is so difficult to calculate for an ill-conditioned matrix, we'll instead use median first passage time to compare our Monte Carlo simulation to our exact calculation. The condition we're solving for is a little bit different there in equation 14, but it has the advantage that we can just multiply the matrix from 15 again and again, and in a strategy of repeated matrix multiplication, we're able to binary search for the median first passage time because our trap state, we know, has monotonically increasing occupation. To test our median first passage time algorithm, we selected a short sequence and chose a metastable structure on the left and its minimum free energy structure on the right as a destination state. This is in fact the same short sequence you saw earlier in the diagram of the 100 most stable structures and the barrier tree for a short RNA. Now let's see how our median first passage time algorithm performed for the small RNA. On the left, I have a plot of the density of states of this short RNA, and you see that there's very few low energy structures available, and then around 0 to 5 kcal per mole we start getting exponential growth as there's a combinatorial explosion of available states. Finally, at high energies we start to deplete the combinatorial number of states available to this short sequence, and the density of states drops back down to 0. On the right, on the same x-axis, I have a plot of the calculated median first passage time compared to the simulated median first passage time in red. On the left, because there's no pathway available at these low energy thresholds, the result is infinite. As we hit the saddle point, we see that I overestimate the median first passage time because I haven't considered higher energy states. Then, in the region of exponential growth, I see that my exact calculation converges to the simulated median first passage time. I would have done the exact calculation for even higher energy thresholds, but the problem is that multiplying large matrices is an expensive computational operation, and it just was not practical. Now I'll explain to you diagrammatically our free energy Arrhenius barrier finding algorithm. For the cartoon energy landscape in part A, I have 3 local minima: a starting basin, an arbitrary neighbor, and a target ending basin. These are separated by 2 barrier states. You see one of them starred in purple, and one of them is the very high energy state with no star on it at all. You notice that the barriers also have a free energy equal to the energy of the single component state. In general, this does not have to be the case. If there were more than one state in the barrier, then the barrier free energy would be lower than the energy of any of the states. In the first step of the algorithm, the starting basin sees that its lowest barrier that it could cross to reach a new basin is the purple starred one. So our program merges the start and the arbitrary neighbor into a single state. In the next iteration, it now has a new starting basin in part B, and it sees that the lowest free energy barrier it can cross to get to the ending state is now starred in purple. When these two are merged, it's considered to have reached the ending state, and the algorithm ends. At the end, we report the highest barrier we ever crossed to reach any neighbor. This is the rate-limiting step in our process, and this is the Arrhenius barrier that we report. You may be wondering, was it actually necessary to consider the entropy of both the barrier and the basin? Maybe I could have just taken the local minimum in the basin and considered the entropy of the barrier. Or maybe I could have taken the entropy of the basin and considered only the saddle point along the barrier and gotten just as good an estimate. Well, Vienna RNA uses the local minimum and the saddle point, and you see those points in black. If you use only the rate-limiting barrier, which means that I'm going to include the entropy, but use the local minimum of the basin. Of course, that only decreases the barrier height I have to cross, because if you add more states to a system, you're only going to decrease the free energy. On the other hand, if I use the saddle point and then I allow the basin entropy to come into play, I only decrease the free energy of the basin and increase the height of the apparent barrier. You can see just visually that these red and green distributions are weakly correlated compared to the black and blue ones. And the blue one is the one that uses my algorithm, where we use both the entropy of the barrier and the basin. Now let's see how this algorithm performed on a set of systems we're actually interested in. We selected a set of random sequences that exhibited a dual hairpin topology, similar to the anti-terminator and terminator hairpin that we looked at in the XPT riboswitch. We then let Vienna RNA's barriers program, that used only the local minimum and a saddle point, calculate its barrier, and we used our free energy aware algorithm to calculate the free energy barrier. Kinfold simulations were run and reported a mean first passage time over 100 simulations that's plotted on the y-axis. Visual inspection alone will show you that our algorithm provided a more tightly clustered set of predictions around the expected trend line than did Vienna RNA barriers. We repeated this test for two different types of topologies, dual hairpin and random, and for two different types of dynamics, Kawasaki dynamics, which we did not discuss here, and metropolis dynamics, which we did. We then saw how well the barriers method and the free energy aware method that we developed fit the Arrhenius rate law. The normalized mean square error for barriers program was always higher than that for our free energy algorithm, but it was only modestly worse for arbitrary topologies. However, for the topologies of interest, our algorithm provided a substantially better agreement with an Arrhenius rate law. I hope that in this talk I've convinced you of three things. One, that metastable states are important to the function of many biopolymers, such as riboswitches. Two, that determining the energy barrier between metastable states is a computationally difficult problem, and an Arrhenius rate law is a reasonable heuristic that can help us understand this. Finally, that the high-energy pathways are important for deciding the lifetime of RNA metastable states. What I haven't told you is that our algorithm is extremely versatile and can be used in principle on any system with both a notion of adjacency and where it is possible to enumerate all of the states below a certain energy threshold. There are some things that could make this even more powerful, however. Coarse graining or projection of the energy landscape onto an order parameter might help us control the combinatorial explosion of states around the point where high energy states start to become important. The other possibility would be to use some pathway sampling so that we can ensure that we only consider the important barrier states and not a lot of states that aren't going to help our system evolve any closer to the destination trap. I hope you found this discussion of the RNA barrier crossing problem illuminating. And if you would like to see more about this, please look for our upcoming paper in the Journal of Statistical Physics, Biophysical Methods Special Edition. Thanks.